Great. Thank you all for coming to the current seminar hosted by CAMS and the math department at AUB, and for the number theory research unit. Our speaker today is Professor Sol Friedberg at Boston College. I've known Sol for, I don't know, nearly 30 years now. Time flies. And have always enjoyed talking to him and listening to his talks. Sol is an expert in all aspects of the Langlands program, bringing together number theory and representation theory and automorphic forms. The Langlands program itself was formulated in the 60s. There were precursors by various other mathematicians before that, but Langlands somehow had a large vision of how one should tie all these ideas together and what was a reasonable approach to focus on some parts of the problems or to find certain ways of doing some of the proofs. Much of the work is still conjectural, but a lot has been proved even so throughout this time, and it's also served as a guiding philosophy for lots of modern number theory. So Sol, thanks so much for agreeing to talk, and we look forward to hearing your talk on the Langlands Program, Introduction and Recent Progress.
So thank you for the kind introduction, and thanks to American AUV for providing this opportunity to speak. Shukran. It's really a pleasure to see so many dear friends and have the chance to talk. So I'd like to mostly give an introduction to the Langlands program. And it's a big program, as Kamal said, and so maybe won't introduce all of it, but I'll try to give a sense of the flavor of it at the expense of some details. And then in the last bit of a talk, I'll try to give a sense of some recent progress. But my real goal isn't to focus on the recent as much as to give an overview, because it's such an important part of number theory that I think it's really valuable to have it in your mind as you see the research in the field. So to begin with, let me start with a Galois extension, a finite Galois extension, K over Q. And I should say that I actually wrote this out, so I have a PDF, but I think it'll be somehow more engaging in spite of my poor penmanship if I try to do it live. So I hope you'll forgive the poor penmanship, but the benefit is that if you have questions, please, I welcome them and you should feel free to ask. And so we have, of course, the Galois group, and, we want to focus on understanding, whatever that means, the Galois group of K over Q. We know that's an important group. And then what we might do is follow the work of representation of scholars, mathematicians in the late 18th, early 19th century, and we might maybe the timing isn't quite right about that. Sorry, it's late 19th, early 20th century. What we might do with a finite group to understand it is consider a homomorphism, I'll call it rho, which takes that finite group and sends it to a group of matrices. So I'll send it to the invertible linear transformations of V, a complex vector space. And again, I'm just doing something, say, finite dimensional, the dimension of the vector space is n. Okay, so with this map, with this homomorphism, then Artin, in the middle of the 20th century, attached something that allowed us to study it by finding an analytic object or a function of a complex variable. So he attached a Dirichlet series, LS rho, sum from 1 to infinity an over n to the s. It converged for the real part of s sufficiently large. In fact, he had a more precise information about that he established. But here's the definition that he gave. Okay, so what we'll do is build elements in the Galois group out of prime numbers. And so it's a fact from number theory that if P is a prime number, prime integer, then for almost all of them, I'll put this little condition which you can work around, but the condition is that it's almost all primes, it's unramified in K, so that just rules out a finite number of primes. Then, in fact, there is a conjugacy class in the Galois group that you can make. I'll call it Frobenius P in the Galois group. And exactly how you get it is something that's handled in algebraic number theory, and it's not going to be critical for us, but there's some natural way to build up the Galois group by attaching conjugacy classes to prime numbers. And then what Artin proposed is to define LS rho, this function of a complex variable, again, sufficiently large. He defined LS rho to be the product over all the primes. And here I'm only telling you about the story for the unramified primes. And what he did is he took that conjugacy class and considered the characteristic polynomial. So that's the determinant of the identity on my vector space minus rho of the Frobenius. So I take that semi-simple conjugacy class, move it to a collection of invertible matrices, and then study the characteristic polynomial and multiply that by p to the minus s and take the inverse. Okay, and so here each factor is of degree n in p to the minus s. So in the denominator of this polynomial, there's an inverse to the right of your screen there. Maybe it didn't come out too clearly, so I'll rewrite it. Okay, but each factor in the denominator is of degree n in p to the minus s. It begins with 1. And this is the fact that it's a conjugacy class doesn't matter because they all have the same characteristic polynomial. Okay, and there's actually a way you can include the remaining primes as well, but that's maybe a technical matter we don't need to get into. You have to reduce V to the subgroup fixed under the inertia subgroup. Okay, but let's sort of see what you might get from this. And I'll give 2 examples, but the first one here, let's just do the easiest case. K equals Q. The Galois group is a 1-element group, and so rho is just trivial. So this Frobenius of P is just the number 1. Rho of Frobenius of P is just the number 1. And in that case, LS rho is exactly the Riemann zeta function. Because it's the product over all the primes of 1 minus p to the minus s inverse. Product over p, 1 minus p to the minus s inverse. So Artin is proposing some vast generalization of the Riemann zeta function that comes out of arithmetic, comes out of this Galois group and homomorphically moving it to a group of matrices. Now, in this case, this object we put in some Archimedean factors and we know that it has analytic continuation and functional equation, but analytic is really meromorphic. So with a pole at s equals 0 and 1, okay, and so it's not actually an entire function, but Artin conjectured that this is the only way that we would get a function of s that actually is not entire. So Artin conjectured that if rho is irreducible, so it's a representation that can't be broken into pieces, and not trivial, so it's not the example I just showed you, then this function, which only converges for the real part of s greater than 1, I already proved that, this function actually is entire. And, when you have an entire function, we can use all our methods of complex analysis to analyze it. So it's very appealing to have entire functions. And this is a famous conjecture of Artin. So there are 2 famous Artin's conjectures, and this is one of them. Okay, so let me give an example. And I'll choose K equals Q adjoin I. And the unramified primes are the odd integers. And it's a little exercise in algebraic number theory that while the Galois group has two elements, it has the identity and has complex conjugation. And you can say exactly when it's the identity and when it's has complex conjugation. And it's the identity if -1 is a quadratic residue, mod P. And so that's the first case. And the second case would be that it's not a quadratic residue, then you get complex conjugation. All right, so we might imagine doing the sort of obvious thing with this two-element group, the Galois group, namely we'll send the identity to 1, we have to. And so the only interesting thing to do is to send complex conjugation and send it to -1. I mean, it's an element of order 2, so we'll send it to -1. And in that case, LS rho, you can write it out, and it turns out to be a Dirichlet function. I'll call it LS chi, where chi of P is just -1 over P. Okay. And so here's a fact. These Dirichlet functions were studied long before Artin. They came up in Dirichlet's proof of the primes and arithmetic progressions theorem. And so he had to study them. He had to continue them. And in fact, this is an example of a function defined for real part of S greater than 1 by a series, which has continuation to all S and in fact is entire. So this is an example of Artin's conjecture in action. And it's maybe the signpost to what you might hope happens more generally. Okay. So in fact, Artin extended this to all one-dimensional representations to characters. So if the group is abelian, all the irreducible representations are one-dimensional. And so maybe I'll write that down. Artin extended this to the case, say the K over Q is abelian, where all the irreducible representations are automatically one-dimensional. And he showed that you, in general, get a Dirichlet function, or if I were to change Q to a number field, I might get some other kind of L function attached to a Hecke character. And so he extended this, and he found something similar. And this goes by the name of Artin reciprocity. So it's a deep fact, and it's an important fact that that these Galois, these L functions based from rho, based from Galois representations, match objects coming from harmonic analysis on Z mod NZ, coming from analysis in some broad sense. Okay, so that's the introduction. And now I want to tell you Langlands' incredible idea, which allows you to get a handle on Artin's conjecture in a different way. And so there's a lot I'll need to explain, but the rough idea is that if rho is not one-dimensional, then LS rho should actually match something called an L function. And to first, this is meant to be a talk for a general audience. You may not have seen L functions, but you might think about it as something coming from harmonic analysis on GON. So so here, if you remember that dimension of the vector space, which we took invertible linear transformations of, was n. So if it's one-dimensional, we get GL1, and you get these L functions from classical number theory. But if rho is not one-dimensional, Langlands proposes that these LS rhos should match L functions coming from analysis, coming from a sort of very different part of, on the face of it, of mathematics, coming from analysis, harmonic analysis, and a little bit more carefully, they are attached to automorphic forms or upgraded versions of those called automorphic representations. And so the harmonic analysis is basically this Hilbert space. Roughly speaking, it's square integrable functions on GLNR that say are invariant under R cross the center. And there are also square integrable functions that are invariant under a discrete subgroup of SLNZ, or GLNZ if you'd prefer, of finite index. So let's see. So what to say about this? We're used to studying Hilbert spaces. Spaces of square integrable functions, and GLNR is a very big object, but we might mod out by something to make it a bit smaller. And when we mod out by something like GLNZ or SLNZ, that's a discrete subgroup. And a lot of experience says that when you have something discrete that is sort of isolated points inside of something bigger, that's a number theoretic situation. So the fact that I'm going to take functions on L2, on GLNR that are invariant under a discrete subgroup puts us in the realm of number theory. And this is not obvious, but this is a big insight of Langlands, building on a bunch of other work that came before studying such functions. And so the insight of Langlands is that arithmetic should be related to analysis, to harmonic analysis on groups, GLM. And now the process of going from harmonic analysis to L functions is really at the heart of automorphic forms, so is certainly part of the theory of automorphic forms. And I don't want to explain it in detail today. I don't think because there are other parts of the story that I think I want us to focus on. So it's part of a theory of automorphic forms. And I do want to just say a little bit about it to just get the vocabulary involved. Let me note that we have that Hilbert space, and the Hilbert space has an action of GLNR. So the group acts on the right on the Hilbert space because the Hilbert space has some sort of maybe conditions that'll take some time to understand, some invariance under a discrete subgroup, but that's on the left. And if I just imagine G in GLNR acting on the right, I can make the new function whose value is just the old function translated on the right by G. And because I'm translating on the right, it doesn't mess up the left invariance properties. So I have a group acting on this Hilbert space. And what we might do is look at an irreducible subspace, pi, and for many pi, I guess I'll say that, for many discrete pieces. So it turns out that this L function LS pi, which you attach to pi by the theory of automorphic forms, so that's the symbol I'll use for the thing coming from harmonic analysis, LS pi, the amazing thing is that it's actually entire. It's not obvious. It's a whole theorem that this function, which is, again, a product over primes for real part of S sufficiently large, has continuation and is entire. Okay, so in fact, it looks an awful lot like the LS rows. It has the same degree factors and for almost all primes. And so Langlands conjectures that if, again, the dimension of my representation rho is n, and rho is irreducible, there is a cuspidal pi. Cuspidal is the condition that gives rise to an entire L function. And the point is that I take the object from algebra, or from arithmetic, maybe I'll say, arithmetic, coming from Galois theory, and it will match an object coming from harmonic analysis on groups. And if we knew that, that would imply Harton's conjecture. So Langlands has given us a very concrete direction to go to try to prove that these things coming from arithmetic have the desired properties by matching them to things coming from harmonic analysis on groups. And that matching, because the things on groups can be analyzed in different ways, allows us to learn something about the arithmetic objects. So this turns out to be a wonderful and deep conjecture. You might ask if these are exactly the same objects. We just somehow encountered two different things. In two different ways, we're building the same objects. But a word of caution, there are more pi's than rho's for a given n. And Langlands expresses it by saying that most pi are expected to be transcendental. And he doesn't mean that in the sense of a different, countability in the real line or something. He means that in the sense of they are really not coming from any aspect of arithmetic. And so, for example, in the very first case for, say, SL2R or GL2R mod SL2Z, you can write down and work with analytic objects, Moss forms, which we can find on a computer, but we don't have any way to construct them. We only can find strings of digits that capture their Fourier coefficients. And so these transcendental objects are, like most transcendental objects, a bit mysterious. Okay, so that's one comment. We also might sort of say, well, what about the arithmetic objects? And a whole other part of the Langlands program, which is important to mention, the arithmetic objects the rows often can be constructed from algebraic geometry and from geometry, often arise from Shimura varieties. And the idea is there's some cohomology space upon which the Galois group acts. And so there's some very natural way of making a representation out of these geometric objects. And so there's a whole part of the Langlands program about Shimura varieties. And I'm not going to talk about that. And I should also say that this caution I gave is only for number fields. So for function fields, it's not, it's expected to be a different situation. And so there's been a lot of work done with function fields where you have both the geometry of some algebraic curves, and you also don't have these transcendental objects to worry about. But I'm not going to talk about either of those themes, but I did want to put them in front of you because they're also part of the story. And I think if I'm trying to give you an overview of the story, it's helpful to do that. Okay. Maybe I should pause for a second and ask if there are questions before I go on. Please just unmute if you have a question. Okay. There's part of a story that we've talked about that we can learn about algebra from analysis, but there's a whole other beautiful part of Langlands' vision, which says that we can learn about harmonic analysis on groups, analysis from the algebra. So also, we can learn about but I'll just describe automorphic forms by harmonic analysis on groups. Again, it's really groups modulo discrete subgroups, just to, but I'll just be a little bit more terse in just say harmonic analysis on groups from arithmetic. And then again, this is part of Langlands vision. And so the idea is that there are sort of very natural things to do, natural constructions in arithmetic. And I'll give you some examples. So you'll see it's really the arithmetic of these specific objects, these Galois representations. And Langlands always proposes that when you can do something on the arithmetic side, that there should also be analogs on the harmonic analysis side. So this is sort of the best kind of dictionary where each side tells you something about the other. So just to give an example, let's see. So if row one, so if I have two of these objects, so there's lots of examples that you can give that are important parts of the theory, but let me just give one of the examples. If we have time, I can give more. So imagine that I have two representations. I'll call them row one and row two. So row one goes into GLV1 and row two goes into GLV2. Okay. Then it's really very easy to take the tensor product and it'll just go into the tensor product of the two vector spaces. So if V1 is dimension N1 and V2 is dimension N2, this would be N1, N2 by N1, N2 invertible matrices. So that's a much bigger finite, a much bigger group of matrices, still finite dimensional, but I just make the tensor product representation. I act on V1 by means of row one, I act on V2 by means of row two. So it's easy to take tensor products. Okay. And now row one is supposed to correspond to an automorphic form on, I'll say, GLN1. So here A is automorphic forms or automorphic representations, and N1 is the dimension of V1. And row two, according to Langlands, is supposed to correspond to an automorphic representation on V2, on GLV2. And just to make it more concrete, I'll say GLN2, where N2 is the dimension of V1. So while this row one tensor row two, if we believe Langlands, should correspond to an automorphic representation on GL N1 times N2, which is that's the V1 tensor V2 space, okay? And invertible linear transformations. So he proposes that we should have this correspondence. And then he says that more generally, if pi1 is anything on GLN1 and pi2 is anything on GLN2, this is one of these things coming from harmonic analysis. They might be arithmetic, they might be transcendental, but if you give me any things from harmonic analysis on N1, GLN1 and GLN2, then there is some object that corresponds to it, pi1, some kind of a tensor, I'll make a little box maybe, in automorphic forms on GL N1 times N2. Oh, and in the sense that the L functions match. So the L functions match. That's sort of how we know that we have the right object. And this is really, on the face of it, okay, sure, sounds like it might be possible, but it turns out to be really a hard problem. So, i.e., you sort of might think about, taking functions on L2 of GLN1. I'll use maybe a bracket for that complicated quotient I was writing down before. And I might have some kind of harmonic analysis piece on one group of matrices and some kind of harmonic analysis piece on another group of matrices. And for the irreducible constituents properly assigned, so I'll put a little dotted line. I don't quite, I mean, it's described very specifically. That somehow I should have harmonic analysis on these groups all being related. And it's not at all obvious. I have some discrete subgroup of GLN1R, some discrete subgroup of GLN2R. How do I make a discrete subgroup of GLN1N2? That's a much, much bigger group, 3 by 3 and 4 by 4. And now I'm doing 12 by 12 matrices. It's a much bigger group. And it turns out that it's really a hard problem. So this construction is conjectured in general, but is only known in small cases. Okay, there are a bunch of similar constructions. So there are other constructions in algebra, such as composition of homomorphisms and induction and restriction of representations. Again, should have analogs. And this is conjectured, known in maybe some cases, and there's just a tremendous amount that we don't know as well. Okay, now all this has been about GLV, and so you might sort of ask yourself, what about other groups? Than the general linear group. So sort of I might be thinking about a symplectic group or an orthogonal group. And so suppose that on the Galois side, my Galois representation, it does go into GLV1, but it actually goes into, maybe I'll call it GLV, I'll drop the one. It goes into a subgroup of invertible linear transformations of V. And the way that can happen is your homomorphic image might fix a symplectic form or a symmetric bilinear form. And so I would naturally land inside of a symplectic group or an orthogonal group. Okay, so maybe that's the case. And I mean, very specific kinds of G. We don't need to get into the details, but if you think about symplectic and orthogonal, you have the main idea. And then Langlands once again proposes that there is one of these harmonic analytic objects, an automorphic representation. And you might think that I just take the same group G, but it's a slightly different thing. I take the dual group of G, so LG is the dual group. And there's a way of involving the Galois group where I really would write LG, but I'm not going to get into that now. So I could maybe put the Galois piece in a slightly different way. But the point is that what I do is that, say, if I were to land inside of symplectic matrices, what I actually get is actually the automorphic object should be on a different group, SO2n plus 1C. And similarly, the L group for SO2n plus 1 would be SP2nC, where SP2n means 2n by 2n symplectic matrices with respect to a symplectic form, so not degenerate symplectic form, so that there's a slight subtlety in terms of different groups. Okay, and this sort of comes out of a theory and is natural when you sort of see enough, but this business of the L group has to do with switching long and short routes. And there's some reason why that happens. But this business of passing between a group and its dual group has become omnipresent in mathematics. In particular, it plays a big role in mirror symmetry. Okay, so now I can go a little bit farther. So let's suppose I have one of these guys. And just for concreteness say it goes into sp2nc contained in gl2nc. Okay, so it happens to land in this subgroup of gl2n of matrices that have an extra property that they stabilize some natural algebraic object on the underlying vector space, some symplectic form on the underlying vector space. So on the one hand, LS rho is supposed to match LS pi, where pi is on the dual group to sp2n, which is to say SO2n plus 1. So there should be some automorphic form or representation on SO2n plus 1, 2n plus 1 by 2n plus 1 orthogonal matrices of determinant 1, which matches it. Okay, that's the idea that I just mentioned. But on the other hand, I'm working too hard here. I could just forget that the thing is inside the symplectic group. It goes into GLN. So on the other hand, or maybe I'll call this pi 1. LS rho is also supposed to be, so on the other hand, I'll just forget, goes into a subgroup of GL2NC. I'll just forget about that. It goes into GL2NC. So this LS rho should also match something which is an automorphic representation on GL2N. So I have rho appearing in harmonic analysis on two different groups. I have SO2n plus 1 and GL2n. And once again, Langlands says this story for arithmetic should be the signpost to a story for general harmonic analysis. So Langlands conjectures map from any automorphic representation of SO2n plus 1 to, it may be cuspidal, so maybe with some hypotheses that I'm not going to give, to an automorphic representation of GL2n. So once again, a harmonic analysis on totally different groups, different size matrices, really different groups, they're supposed to have harmonic analysis that's linked, and again, such that the L functions match. Okay, so this has a funny name. It's called the endoscopic transfer. It's an example. You could also do it with symplectic groups and the orthogonal groups switched, for example. But the idea is that there is a piece of the automorphic spectrum of GL2n that really comes from a different group, and that is sort of, so endoscopic is this medical procedure where you look inside a person's body, but here we're looking inside GL2n and finding pieces of it that really come from something smaller. So that's the name, which actually was coined by my colleague at Boston College, Avner Ash. So he was the one that came up with that word. Not surprisingly, his spouse is a physician. Anyway, so there you go. So that's a conjecture, and this conjecture was proved by Jim Arthur, and it uses the full generality of the trace formula, started by Selberg, but extended vastly by Arthur, and it also uses the fundamental lemma for Nagot, for which he won the Fields Medal. it uses quite a bit of additional work of many people, but especially I think it's appropriate to mention Wallis Bourget, for which you won a Clay Research Award, and Arthur received the Steele Prize for Lifetime Achievement from the American Math Society. So even though this is only one case, this case has so much structure to it and turns out to be very deep that you can tell these awards were properly given, in my opinion, and they reflect that to prove this matching of harmonic analysis on two different groups is remarkably subtle and takes, it's really been the work of a generation to accomplish it. And it involves ideas from many, many fields, and certainly including algebraic geometry. Okay, so that's some endoscopic transfer. And the first proof is given by Arthur. But it turns out that there is another approach. Arthur proves along the way many other important facts, but there's for this endoscopic transfer, the thing that Langlands conjecture, there is another approach, and it's roughly speaking, learn enough about L functions. Okay, so given pi1, say an automorphic form on GLN1, and pi2, an automorphic form of representation on GLN2, we discussed this conjecture that you can make a pi1 cross pi2 on GLN1 times N2, and that's hard. That's mostly not been proved. But it turns out that it's a lot easier is to study the L function, again, the thing that on the automorphic side mimics Artin's L function. And I'll take away the box because I'm not saying there's something on the big group. It turns out that if you just have something on GLN1 and on GLN2, you can get the analytic properties of the of this Dirichlet series that you would hope to have behave nicely. And it turns out that that's much easier. So this goes back to Rankin and Selberg for N1 and N2 equals 2. And then it's Jacquet, Piatesky, Shapiro, and Shalaika for general N. And there's also a bit of completion work at the Archimedean places by Cogdell and Piatesky, Shapiro. That's also quite important. Okay, so these L functions are sort of easier objects than proving that the full harmonic analysis matches, and then it's a theorem called the converse theorem. If enough L of S pi1 cross pi2 are properly behaved, maybe I should maybe say given pi1, which we don't know is automorphic, possibly automorphic. So maybe one of the things we're looking for, given pi1, possibly automorphic, if enough of these LS pi1 cross pi2 are properly behaved, then pi1 is automorphic. So in other words, this is a criterion for knowing whether or not we have something in harmonic analysis that's a bit easier than realizing it in a Hilbert space. There's sort of a way that gets around working with these really large Hilbert spaces that allows us to realize it. And this goes back to Weil, and it was really a fundamental part of why he believed and supported the Shimura-Taniyama conjecture that every elliptic curve is attached to a modular form of weight 2, because he was able to prove a theorem, which was a first converse theorem. So V is again for n equals 2. And then the general case is Cogdell and Piateschi-Shapiro. So this L function approach to endoscopy is very different than the trace formula. And Cogdell, Kim, Piateschi, Shapiro, and Shahidi, they proved endoscopic transfer via L functions. And remember, endoscopic transfer says you start with something on one group and you move it to the general linear group, you move it to another group. And they proved endoscopic transfer via this big method from automorphic forms of L functions, but they needed to make a hypothesis, provided, say, pi on, in our example, SO2n plus 1, I think I called it pi 1, has a certain property. For the experts is genericity in the sense of having a Whittaker model. So it's not generic in an algebraic-geometric sense, but it has some special property, which many automorphic representations do, but also, unfortunately, some don't. And that's where things stood for 20 years. And then the recent work is that together with Yunxing Kai and Eyal Kaplan, sorry, I think I have the order of the David Ginsburg, to get my alphabetical order properly, and Eyal Kaplan. And then there's a lot of additional work. There's a piece that was done by Kai, myself, and Kaplan. And then there's various pieces of Gurevich and Kaplan. So there's sort of a big idea and a lot of follow-up work. And there's even a piece which is Gurevich, let's see, Kai, Friedberg, Gurevich, and Kaplan. So there's all these different papers with different parts of it. But the key part is this paper we wrote in Invenciones that gets us started. And we use the L function method for all of automorphic representations on SO2n plus 1 or SO2n or SP2n. So in fact, the trace formula and these beautiful, brilliant, but also very difficult ideas of Arthur and Nagot and Waltz-Berger and quite a few others, turns out there's a way around them. If you want to prove Langlands' vision that automorphic forms, that harmonic analysis on different groups is related, then the L function method, which goes back to Vey and with the vast extension by Cogdell and Piateschi-Shapiro, it works quite generally. And at the moment, we've done split groups. I think our methods could be extended to quasi-split groups. So there are cases that Arthur handles that we don't, but there's also a case that we handle that Arthur doesn't. We actually handle G-spin, which is not, in fact, handled by Arthur. And I think the real lesson isn't who got there first, though I know people want to think that way, but that there are these two different methods that both can address the problem in this case, but that the big vision of Langlands, that harmonic analysis on different groups is related, and that motivated by constructions in algebra, we can learn something. This is mostly untouched. It's a vast construction and a very interesting one. The L functions that you get also have very interesting special values described by conjectures of Deligne and related to arithmetic. Understanding the L functions tells us distribution statements such as Ramanujan's conjecture. So there's a vast edifice here that's based on the ideas of Langlands, and I'm pleased to have had a chance to give you an introduction. I think that's a good place for me to end, so we have a few minutes for questions if anybody has them. Thank you.
Thanks very much. I mean, consider virtual clapping. It's hard over a screen. The floor is open for questions from the participants. I think the easiest way is if one person at a time unmutes themselves and asks a question, if you need some help in prioritizing, you can instead raise a hand or write a question in the chat.
My questions are very welcome. Please,
Yeah.
I know I talked a bit fast there. And if there's anything that you want to ask about, I welcome that.
Right. But I mean, just unmute yourselves and ask. You don't have to wait for permission. I'm looking carefully to see if anyone has unmuted themselves, and I'm waiting to see if someone writes something in the chat. I mean, I can ask a technical question, which is that in your recent results, do you and your collaborators also get a good handle on the image of the endoscopic transfer? Because that's one of the things that the trace formula gives you that tends not to come out well in Rankin-Selberg.
Right. Well, I mean, I guess you can tell something from L functions, right? So when you look at symmetric square and exterior square L functions, you can pick up whether things are coming from lifts by means of that. So we would have nothing to say beyond that. So these endoscopic character identities, say of Arthur, that's not something that we're touching. That really comes out of a trace formula.
Yeah, that's the one thing that the trace formula seems to get that is hard to get by other means. Yeah.
Oh, absolutely. I mean, it gives a lot. It definitely gives us some important additional information, which is quite critical in understanding, say, L packets. There's more than one object on these other groups with a given L function, and so there's important discussions to be had about that.
I just have a small question.
Please.
Yeah, well, if you interchange the two groups, SP2N and SO2N plus 1, you get another map, right? And if you like compose the two, you get I'm not sure, either a map from related to GL2N to GL2N plus 1 or the other way around. And I was just wondering if this was also conjectured to be something simple like restriction or, something like that.
Thank you, Joseph. I'm going to answer your question, and then actually I realized I have a little more that I can offer to Kamal. But so the L group for SO2N plus 1 is SP2NC. The L group for GL2N is GL2NC. And there's a natural homomorphism just given, sort of very simply by inclusion. Just forget that you happen to have this extra structure of a symplectic group. So that will allow us to map automorphic representations on SO2N plus 1 to automorphic representations on GL2N. Unfortunately, you can't go backwards, so you can't expect that every automorphic representation of GL2N comes from SP2N. That's a little bit too much to hope for. But I think your question also does point out something very interesting. So you could also ask, if I start with pi here and say it has the right L function property, so it does come from a symplectic group, how could you find, I think I called it pi 2, how could you find the pi 1 that comes to it? How could you actually make pi 1 from pi 2? And I think that's also in the spirit of your question, Joseph. And so there is a beautiful answer of Ginsburg, Rawls, and Sudri. They call it backwards. They call it automorphic descent, the backwards lift. Sort of you go backwards, instead of taking pi 1 and building pi 2, you go from pi 2 and build pi 1. So you actually can do that. And it's a beautiful construction in automorphic representations. And in fact, I have the book right in front of me. Let's see, I don't know if you can see it there, but here's this book from not that long ago called The Descent Map from Automorphic Representations of GLN to Classical Groups by World Scientific. It's right on my desk, along with Arthur's book, by the way. Those are the two books on my desk. So there you go. And so, yeah, so it's a great question, and there is an answer, and it's a beautiful answer. I did also think of one other thing I should have said to Kamal. I mentioned that there are different automorphic representations with the same L function on these classical groups. And so you could, building on Joseph's question and on your question, you might say, not just can I build pi1, can I get all the automorphic representations on sp2n? Can I build the entire L packet? And I think that's in the spirit of your question, Kamal, at least a little bit. And then there's a beautiful theory, they call it backwards descent, which starts with these constructions that we did together, and actually builds it up to build not just the generic element of the L packet, which is what's in that book, but to build the entire L packet. So it builds all pi1, which lift to pi2, and that's work of David Ginsburg and David Sudry, who for many years, when Steve Rollis worked with them, were called the Davids, plural. And so this, sadly, Steve Rollis has passed away, a great loss. And but Ginsburg and Sudry are still doing wonderful things together. So so there is that construction, which I think is a little bit in the spirit of your very nice question.
Couple of more questions. Well, a quickie, because I'm a bit worried about that I can guess what the answer is going to be. What hope is there for non-endoscopic transfer, or even just L functions for things like, you know, high symmetric powers for even GL2?
Right.
Do we even have a program for where to go next and trying to build?
That's a wonderful question. So the answer turns out to be very different for the things coming from arithmetic, cohomological automorphic representations than in general. So symmetric powers, which of course would be wonderful to do, have been done for holomorphic modular forms using really the arithmetic constructions. But if I wanted, say, to apply them to a MOS form, a level 1 MOS form, something on SL2R that's invariant under SL2Z and an eigenfunction of the Laplacian, the first sort of transcendental object you might want to study, that's certainly part of the spectral theory of this Hilbert space, then it's much harder and we don't know how to do it. But when something has cohomology attached to it, then maybe there are other methods. In fact, not only maybe, but there genuinely are other methods that are very powerful. But in general,
that limits the groups. That limits the groups quite a bit.
Absolutely. And so Langlands has a vision of beyond endoscopy. He wrote a famous paper about that, and people are working on it. And there are some interesting ideas kicking around, I think it's fair to say. And so there are people working quite hard to go beyond endoscopy, but I think it seems, even though, you know, this case is just sort of the easiest case, you just have the same L functions, they just match. And when you throw in things like symmetric powers, things get more complicated. At the moment, they're so much more complicated that we don't really know how to do them, except in some very small cases. And I think it's clear that it's a hard problem for number fields. For function fields, it might be more tractable.
Yes, fair enough.
Yeah. I should say there are other parts of a Langlands program I haven't talked about. There's a p-adic Langlands program. There's a relative Langlands program. There's actually lots of ideas that are being generated by this that are very exciting, and you know, people are working on them extensively. But it all, I think, starts from this Langlands program that I talked about today, and then people keep finding new things to do with these ideas and push them in new ways.
Well, I think I'm going to say thank you very much. We'll leave everything open for about 30 more seconds if someone else comes up with another set of questions to ask. But in the meantime, let's give you another big hand. And thanks so much for your wonderful talk, Saul.
Really a pleasure to be here. So nice to see you.
Thank you so much for the talk, Saul.
Truly my pleasure.
Thank you.
Hmm.